If you were to step out onto the surface of Mars right now, just wearing, a pair of jeans and a t-shirt, you actually wouldn't freeze to death first.
No, you definitely wouldn't.
Right. Because before the cold even really had a chance to register, the moisture in your lungs, the saliva on your tongue, and literally the tears on your eyeballs would just instantaneously begin to boil.
Which is an incredibly grim image, but yeah, it's physically accurate.
It is. And today, in this deep dive, we're taking this highly romanticized sci-fi dream of colonizing Mars, and we're putting it under a very harsh, very realistic microscope.
Exactly.
Because for decades, we've all looked up at that red dot in the night sky and just kind of treated it like this blank canvas for human destiny.
Yeah, the ultimate frontier.
Right. But we've got a massive stack of recent research, mission projections, and biological studies sitting right in front of us today. And our mission is really just to cut through the hype.
To look at the actual science.
Exactly. We want to answer one fundamental question for you. Conditionally speaking, can human beings actually live on Mars?
And I think, that phrase right there, conditionally speaking, that is the absolute linchpin of our entire conversation today.
Yeah, it has to be.
Because when we strip away the glossy concept art of those beautiful domed cities and really look at the raw data, we are immediately confronted with this massive, undeniable paradox.
The paradox of the environment.
Right. On one hand, Mars is unequivocally the most promising destination in our solar system for human life. I mean, it has water ice locked up in its poles.
And beneath the surface too, right?
Yes, beneath the surface as well. It has carbon. It has nitrogen.
So the raw ingredients are there.
Exactly. Those are the fundamental raw ingredients required to sustain biology, at least as we understand it.
I mean, it's a rocky planet. It's not a gas giant that would just swallow a ship whole. And it's not, a pressurized inferno like Venus where it literally melts lead on the surface.
Right.
It has the chemical building blocks we need.
Right.
So the dream makes sense.
The dream makes perfect sense on paper. But, and this is the truth we really have to hold in our minds simultaneously throughout this entire deep dive, Mars is also the most hostile environment we could possibly try to inhabit.
Yeah.
It has radiation that absolutely never stops. It has an atmosphere that is, frankly, barely worth the name. And it has a gravitational pull that might slowly, insidiously destroy the human body over time.
We have to hold both of those realities at the exact same time. It is the most promising, and it is the most hostile.
Simultaneously.
Yeah. And if you've been following the news lately, you might have noticed that reality is really starting to catch up with the dream.
Oh, definitely.
For a long time, the narrative was that we'd be touching down on the Martian surface in the 2020s. Like, we were supposed to be packing our bags right now.
That was the initial timeline, yes.
But current projections from certain commercial space programs have recently delayed their initial crewed missions. They were aiming for 2026. And now they're pushing those projections out to the early 2030s at best.
And it's not just the crewed missions that are facing these massive reality checks.
No.
There were highly anticipated robotic sample return missions specifically designed to carefully collect Martian rocks and launch them back to Earth.
Right.
Well, certain planned missions have been canceled in favor of prioritizing human exploration. The legislative authorities made a massive pivot in funding, but even with that shift, the timeline is just stretching out further and further.
Which really tells us something crucial right off the bat, Mars is not imminent.
It's not.
And honestly, despite what the loudest voices in the room might try to tell you, it is not inevitable.
No, we have to actually do the work.
Exactly.
Yeah.
So let's get into the reality of it. Let's look at the destination itself. Because when we see those high-resolution pictures from the rovers, it's incredibly deceptive.
It really is.
It looks like a desert in the American Southwest. It looks like you're just standing in Utah or Arizona. You look at those dry riverbeds, and you almost feel like you could pitch a tent, start a campfire, and just watch the sunset.
But that visual similarity is a total trap.
Yeah.
Because your immediate physical reality on that surface would be violently different from anything you could ever experience on Earth.
Okay, let's unpack this.
Okay.
Because the numbers are wild.
Let's start with the temperature. The average temperature on Mars is minus 60 degrees Celsius.
Which, for our listeners who use Fahrenheit, that's roughly minus 76 degrees.
Right.
That is significantly colder than most places in Antarctica in the absolute dead of winter.
It is, but that's just the average. The real danger, the thing that engineers lose sleep over, is the fluctuation.
The temperature swings.
Exactly. Because Mars has such a profoundly thin atmosphere, it completely lacks the thermal mass to trap heat effectively.
Okay.
On Earth, Our thick atmosphere acts like a heavy blanket, keeping the temperature relatively stable from day to night. Mars doesn't have that blanket.
So what does that actually look like on the ground?
Well, you experience wild, rapid temperature swings. At the equator, at high noon in the middle of summer, the temperature right at your feet might actually be a comfortable 20 degrees Celsius.
So around 70 degrees Fahrenheit. That's a beautiful spring day.
Right. But if you were to measure the temperature just at the top of your head, roughly 5 or 6 feet higher, it could be below freezing.
Wait, really? Just a few feet up?
Yes. The heat simply doesn't hold in the air. It radiates immediately back into space.
So your toes are experiencing this pleasant spring day, and your nose is in literal blizzard.
Effectively, yes.
I can't even fathom what that kind of thermal stress does to building materials, let alone a human in a spacesuit.
It's a structural nightmare.
But going back to what I said at the very beginning, the moisture in your lungs boiling, that isn't a temperature issue, is it?
No, it's not.
That's a pressure issue. So to give you, the listener, a visceral sense of this environment, imagine you are standing at the absolute peak of Mount Everest. You are in what mountain climbers call the death zone. Now, take away 99% of the tiny, tiny bit of air that's still left up there. Replace what little is left entirely with carbon dioxide. And then turn off the planet's magnetic shield. That is the Martian surface.
That is a highly accurate and frankly terrifying analogy.
It's a lot to process.
It is. Let's break down the mechanics of that pressure issue because it's vital to understanding the real hostility of the environment. The Martian atmosphere is 95% carbon dioxide.
Okay.
And the atmospheric pressure is roughly 1% of Earth's at sea level.
Just 1%. I think it's hard for people to conceptualize what 1% atmospheric pressure actually physically does to a biological organism.
It comes down to a concept in physics called the Armstrong limit.
Right.
Boiling isn't just about heat. It's about the relationship between temperature and ambient pressure. When atmospheric pressure drops, the temperature required to boil a liquid also drops.
So you don't need a stove to boil water.
Exactly. At the incredibly low pressure of the Martian surface, the boiling point of water drops below the normal resting temperature of the human body.
Which is 37 degrees Celsius or 98.6 degrees Fahrenheit.
Correct. So if you were exposed to the Martian atmosphere without a pressurized suit, the moisture in your lungs, your saliva, the water on the surface of your eyes, they would literally undergo a phase change from liquid to gas instantly. They would boil.
Oh, man.
Not because you are hot, but because there is zero pressure keeping that liquid state stable.
See, I know it's a terrifying mental image, but honestly, to me, that is the thrill of exploring an alien environment.
The thrill.
Yeah, it's the sheer uncompromising physics of it. I mean, it's a world that operates by a completely different set of rules. You're standing on a world that actively refuses to let you exist, and yet human engineering is trying to figure out how to stand there anyway?
Well, it is a marvel of human ambition, absolutely. But we have to ground that awe in the reality of the physics.
Fair enough.
Because the boiling saliva is just what happens if your suit fails. What happens when your suit works perfectly is almost more insidious.
Which brings us to the radiation.
Yes. You mentioned turning off the planet's magnetic shield in your Mount Everest analogy.
I did, yeah.
That is, without a doubt, the ultimate game changer for biology.
Right, because here on Earth, we basically have this invisible force field. We have a molten iron core spinning around deep inside the planet, and it generates this massive magnetosphere, plus we have a thick atmosphere with a protective ozone layer.
We do.
We are incredibly pampered here on Earth, like we don't even think about space weather.
Pampered is exactly the right word. Our magnetosphere acts like a planetary deflector shield, essentially bouncing the vast majority of solar flares and galactic cosmic rays away from the surface.
But Mars doesn't have that.
No, Mars lost its global magnetic field billions of years ago. It essentially cooled down, the core stopped acting as a dynamo, and the magnetic shield just died.
Wow.
So it has no magnetosphere to speak of and no ozone layer, which means the surface of Mars is constantly relentlessly bombarded by deep space radiation.
Like 247?
It never stops. Every second you are on the surface, your body is being penetrated by high-energy particles from the sun and from distant supernovas.
I really want to get into exactly what that radiation does to human DNA, but before we leave the physical environment of the surface itself, we really have to talk about the weather.
Oh, the dust.
Yes, because if the radiation doesn't get you, the dust might. And these aren't just, a windy day at the beach. We're talking about dust storms that can consume the entire planet.
Exactly. Because of the specific atmospheric dynamics on Mars, they experience planet-wide dust storms.
Which is wild to think about.
It is. These aren't local events that blow over in an afternoon. They can literally engulf the entire globe and last for months at a time, just blocking out the sun entirely.
So solar power takes a huge hit.
A massive hit. But the real issue is the dust itself. It is not like Earth sand. It is incredibly fine, almost like talcum powder. And crucially, it is highly electrostatic.
Okay, I read that in the sources, but I need you to explain why it's electrostatic.
Yeah.
I mean, I understand getting a static shock when you walk on a carpet in the winter, but why is an entire planet's dust statically charged?
Well, it comes down to a process called triboelectric charging.
Triboelectric charging, okay.
On Mars, it is incredibly dry. There is absolutely no ambient humidity to dissipate electrical charges. So as the wind blows, these ultrafine dust particles are constantly rubbing against each other.
Just constant friction.
Yes, and this constant friction strips electrons from some particles and adds them to others, creating massive static charges. Because there is no moisture in the air to ground them, the particles just hold that charge.
So it's essentially an entire planet covered in microscopic cling wrap.
That's a really great way to visualize it. Because of that electrostatic charge, the dust clings to absolutely everything. Solar panels, spacesuit visors, airlocks, mechanical joints.
Everything gets coated.
And because the particles are jagged, they haven't been smoothed out by flowing water like sand on Earth, they are highly abrasive.
Like tiny shards of glass.
Exactly. They get into the seals of your suit, they grind down the gears of the rovers, and if you track it into the habitat, it gets into your lungs.
So just to recap the destination for you listening, we have wild temperature swings, 1% atmospheric pressure that boils your blood, relentless cosmic radiation, and jagged, static cling dust storms that block out the sun for months.
It's quite the list.
It really is. And we haven't even mentioned the gravity yet. Mars has 38% of Earth's gravity, which, I'll be honest, sounds incredibly fun at first.
You'd be very light.
Right.
Yeah.
You weigh a third of what you weigh on Earth. You could dunk on a 10-foot basketball hoop with zero effort. You could carry massive equipment around like it was made of styrofoam.
It does sound like an astronaut's playground, I'll admit that. Until you consider what gravity actually represents to the human body.
Right.
Gravity isn't just a force keeping us from floating away, you know. It is the fundamental mechanical resistance that our biology evolved against for millions of years.
We need it.
We do. Our bones, our muscles, our cardiovascular system, they all rely on the constant, heavy downward pull of 1G to maintain their strength and function.
So what happens when you take that away?
When you reduce that pull by over 60%, your body doesn't just enjoy the vacation, it immediately begins to adapt to the new, easier environment. And in this context, adapting means breaking itself down.
Which is terrifying.
It is. But we will get deeply into that physiological toll later, because before you can even worry about the Martian surface, you have to survive the commute.
Which is the perfect pivot.
Yeah.
Because you can't just magically teleport to this hostile desert. You have to get there.
Yes, you do.
And depending on planetary alignment, you are looking at a 7-month journey in a very, very small metal cylinder. 7 months each way.
This is where the logistical and biological realities really start to compound and multiply.
Yeah.
7 months in deep space transit is a profoundly different experience than spending 7 months in the International Space Station.
Because the ISS is basically right next door in cosmic terms.
Exactly. The ISS is in low Earth orbit. It is still largely protected by Earth's magnetosphere. A spacecraft traveling to Mars is out in the deep ocean of space, completely exposed.
And the sources we're looking at highlight a truly staggering statistic regarding that exposure. During those 7 months of transit, the crew is exposed to radiation equivalent to 24 C80 scans every single day.
If we connect this to the bigger picture of human health, a single CA scan delivers a significant dose of ionizing radiation.
Right. Doctors try to avoid them unless necessary.
Medical professionals on Earth strictly limit how many a patient should have in a given year, let alone a lifetime, because ionizing radiation literally strips electrons from atoms in your body.
Which damages the DNA.
Yes, it can sever the strands of your DNA. So to endure the equivalent of 24 CA scans a day for roughly 210 days straight.
I just can't even.
The cumulative damage to cellular DNA is immense.
Okay, I have a naive question here. If we know the radiation in deep space is this catastrophic, why can't we just build the spaceships out of thick lead? Like just wrap the whole crew cabin in heavy metals like a lead apron at the dentist and problem solved.
It's a very logical question. But it runs headfirst into the most unforgiving law of space travel: the rocket equation.
The rocket equation.
Mass is your ultimate enemy. For every single kilogram of lead you add to the spacecraft for shielding, you have to add exponentially more kilograms of rocket fuel just to lift that lead off the Earth and push it all the way to Mars.
Oh, I see.
Lead is incredibly dense. If you built a shield thick enough to stop galactic cosmic rays, the ship would be so heavy that no rocket on Earth could launch it.
So it's like trying to build a bulletproof vest, but the vest weighs 3,000 pounds, so you can't even stand up.
That's exactly it. So engineers are trying to find alternative mitigation strategies.
Like what?
Well, some studies suggest we can mitigate transit radiation by using the ship's own supplies as a shield.
Supplies, like boxes of food.
More like water. For example, lining the walls of the crew's sleeping quarters with the spacecraft's water tanks, or even the fuel tank.
Oh, that makes sense.
Right. Water is dense enough to absorb a lot of radiation, and you have to bring it anyway.
Because humans need to drink.
Exactly. But even with water walls, the crew is taking a massive hit.
It's dark humor, honestly. You are traveling to the most hostile physical environment imaginable, a place that requires absolute peak physical condition to survive, and you arrive there with your cells already irradiated and damaged.
Conditionally speaking, yes.
And it's not just the radiation. Let's talk about the microgravity toll during that commute. Because while Mars has 38% gravity, the 7-month journey there is in microgravity.
Essentially 0G.
Right.
And we know from long-duration missions on the ISS that without gravity, the human body experiences severe muscle atrophy and bone density loss.
Right, they waste away.
To fight this, on the ISS, astronauts have rigorous daily exercise protocols. We're talking lasting 2 to 2.5 hours using specialized resistance machines.
Right, they strap themselves down to treadmills with bungee cords, essentially. So why wouldn't that just work for the Mars commute?
Because even with those extreme countermeasures, they still lose bone mass.
Really? Even with 2 hours a day?
Yes. The exercise slows the degradation down, but it doesn't stop it. Without the constant 247 mechanical loading of gravity, the cells that break down bone simply outpace the cells that build it.
Wow.
Over a 7-month journey, even working out for hours a day, the crew will arrive physically compromised.
So you arrive at this terrifying alien destination. You spent 7 months floating in a tube. You are literally a weaker, degraded version of yourself. Your bones are more brittle, your muscles have shrunk, your cardiovascular system hasn't had to pump blood against gravity, so your heart muscle is literally weaker.
Yes.
And then you have to put on a heavy pressurized spacesuit, walk out into 38% gravity, and start building a colony from scratch.
And we haven't even touched on the psychological toll of the transit yet.
Oh, right, the mind.
We are highly social, earthbound creatures. Being confined to a small spacecraft with a handful of people for 7 months, just staring out into the black abyss, is a psychological pressure cooker.
And it's compounded by the communication delay. This is something I think a lot of people just gloss over when they think about space travel. We are so used to instant communication on our phones.
We are.
But when you are halfway to Mars, you can't just pick up the phone, call mission control, and ask for advice.
What's fascinating here is the absolute limitation of the speed of light.
Right.
Radio waves travel at the speed of light, which is incredibly fast, but space is vastly huge. Depending on where Earth and Mars are in their respective orbits around the sun, the distance between them changes constantly.
Yeah.
At their furthest point, it can take up to 20 minutes for a radio message from a Mars-bound ship to reach Earth.
I want to put the listener in that exact scenario for a second. Imagine you are the commander of this mission. You are 5 months into the journey. Suddenly, alarms start blaring.
The worst-case scenario.
Exactly. There's a fire in the oxygen generation system, or a critical life support valve has just failed. You send out an emergency distress call. Houston, we have a critical failure in Module 3.
And then?
You then have to sit there in the dark, breathing smoke or losing pressure, and wait 20 solid minutes for that message to even reach the headsets of the engineers on Earth.
Yeah.
Then Mission Control has to analyze the telemetry, argue about a solution, and send the technical fix back to you. That radio wave takes another 20 minutes to reach your ship.
It is a minimum 40-minute round trip for a single exchange of dialogue.
That's terrifying.
You cannot have a real-time conversation. You cannot have real-time guidance during a sudden crisis.
You're on your own.
The crew has to be completely 100% autonomous, which is an unprecedented psychological weight for human spaceflight. They are, in a very real, tangible sense, entirely alone. If they make a mistake, Earth cannot catch them in time.
And that profound isolation extends to the supply chain as well. I mean, if something breaks on the ISS, they can put a replacement part on the next cargo rocket and have it there in a few days.
But if a critical component fails on the way to Mars...
You cannot order a replacement.
No, you cannot launch a quick resupply mission because orbital mechanics completely forbid it.
Orbital mechanics.
Yeah.
Meaning where the planets are.
Exactly. Earth and Mars are essentially running on two different tracks around the sun at different speeds. Launch windows from Earth to Mars, the times when the planets are aligned perfectly to allow a spacecraft to make the jump efficiently, only open once every 26 months.
Every 2 years, roughly.
Yes. So if you need something that you didn't bring with you, you were simply out of luck. The sheer impossibility of quick resupply means that redundancy isn't just a nice safety feature, it's the absolute core of the mission architecture.
Everything has to have a backup.
Everything must have a backup, and a backup for the backup.
But wait, if everything needs 3 backups, that adds weight. And as you said earlier, the rocket equation absolutely hates weight.
Exactly. It creates a brutal engineering loop.
How so?
Well, you need backups to survive because resupply is impossible. But backups add mass. Mass requires exponentially more fuel. Fuel adds more mass, which requires a bigger rocket.
Which brings me back to those delayed timelines we discussed at the top of the show. When I look at all of this, the 24 CT scans a day, the fact that water walls might only partially work, the unavoidable bone loss despite 2 hours of daily exercise, the 40-minute communication delay, the impossible supply chain governed by orbital mechanics.
It's a daunting list.
It is. I have to push back a little on even the revised projections. If current projections from certain commercial space programs now place the first crewed missions in the early 2030s, isn't that still wildly, almost dangerously optimistic?
I hear your point.
Given the biological and logistical toll of just the commute, are we really going to be ready to put humans through this in less than a decade?
This raises an important question about our threshold for risk. We really have to frame our answers conditionally. Some studies suggest we can mitigate the worst of the transit radiation. We are actively developing better, more targeted exercise countermeasures for microgravity.
Right.
So conditionally speaking, if those mitigation strategies prove highly effective, and this is a big if an organization is willing to accept a historically unprecedented level of risk to the crew's lives, the early 2030s might be technologically feasible for a simple flags and footprints mission.
Just getting there and coming right back.
Exactly.
If being the operative word, doing a whole lot of heavy lifting there, because surviving the commute just gets you to the starting line. Let's assume, conditionally, that the current projections hold. Let's assume the astronauts survive the 7-month gauntlet.
Okay.
They arrive on Mars, the engines fire, they descend through the thin atmosphere, and they land in the red dust. Now what?
Now they need a home.
Where do they sleep? You step out into minus 60-degree weather with boiling pressure and cosmic rays. You need a habitat.
That is the habitat problem.
Right, because you can't just ship a subdivision from Earth. The rocket equation rears its ugly head again. Every pound of cargo you want to safely land on the surface of Mars requires exponentially more pounds of fuel to get it off Earth, push it through space, and then perform a powered descent to slow it down for landing.
The math is unforgiving.
Shipping steel girders, concrete blocks, or even pre-built heavy metal houses is completely off the table.
It is. And this introduces a concept that is absolutely central to any long-term Mars mission design. ISRU.
ISRU. What does that stand for?
In situ resource utilization. It's a highly technical way of saying living off the land.
Okay.
If you can't bring it with you, you have to build it out of what is already there waiting for you.
And this is where the science fiction is actively, thrillingly becoming science fact. Because we can't bring steel, the necessity of building from Martian materials has sparked some of the most creative biological engineering in human history.
Truly. And biology might actually be the key to architecture on Mars. We are not just talking about digging caves. We are looking at some very recent, very compelling research that uses living organisms to build the colony.
Okay, here's where it gets really interesting. I was reading through the sources, and in July 2025, certain researchers demonstrated something incredible.
The algae experiment.
Yes. They took living algae and they placed it inside 3D printed bioplastic chambers. They then subjected these chambers to simulated Mars-like conditions, the freezing temperatures, the 1% pressure, the specific light spectrum that makes it through the dust.
And what happened?
The algae didn't just survive, it photosynthesized. It produced oxygen in an environment designed to kill it.
The implication of that July 2025 study is profound for life support systems.
That's massive.
It suggests that we don't need to bring massive, heavy oxygen tanks to sustain a colony indefinitely. We might be able to create a localized biological loop.
A closed system.
Right. The algae consumes the carbon dioxide, which, remember, makes up 95% of the Martian atmosphere, so they have an endless food supply, and produces the oxygen the crew needs to breathe.
But it gets so much better than just breathing, you know?
Wow.
It's about actually building the walls around you. The sources highlight another major breakthrough from January 2026.
The concrete.
Yes. Certain studies suggest that there are 2 species of incredibly tough microbes that can actually be used as a binding agent for Martian dirt.
It's fascinating biology.
You feed them, and they excrete a substance that binds loose Martian soil, the regolith, into a material that is functionally similar to concrete.
The scientific process you're describing is called biomineralization.
Biomineralization.
Yes, it's using biological processes to create structural materials. Essentially, certain species of microbes use an enzyme to break down urea, which creates carbonate. That carbonate binds with calcium in the environment to form solid calcium carbonate crystals.
It's biological glue. I mean, think about what that means for a mission profile. You aren't shipping tons of heavy bricks or cement mix. You are shipping a tiny, lightweight vial of dormant microbes.
Which weighs practically nothing.
Exactly. You land on Mars, your rovers scoop up the loose Martian dirt, you mix in the microbes, you give them some water, sunlight, and a nutrient broth, and they literally cement the dirt together at a molecular level.
It's a very elegant solution.
You can use 3D printing rovers to extrude this mixture, layer by layer, and print an entire habitat from dirt, sunlight, and biology.
Yeah.
We are talking about literally growing a piece of Earth on Mars.
It is remarkable.
It is the most elegant, mind-blowing solution to the heavy lifting problem. You print a thick shell of microbe concrete to protect you from the radiation and the micrometeorites, and then you line the inside of that shell with those algae-infused bioplastics to generate your air. It's a living house.
But what about the human body after years of Mars gravity?
Right, the gravity.
Yes, the gravity.
You know, I get so caught up in the brilliant engineering of it all, the living houses, the microbe concrete, the algae loops. It feels like we can just outsmart the planet. Yeah. But you're right, you just perfectly punctured my excitement.
Well, it's a necessary puncture because it forces us to look at the whole picture. Fair. You can engineer the perfect external habitat. You can build a 3D printed, radiation-shielded, biologically looped fortress underground. You can totally solve the external survival problem using brilliant ISRU techniques.
Right.
But that brings us directly to the hardest problem we face. The internal survival problem, the human body itself.
Because the habitat protects you from the vacuum, the cold, and the dust.
Mm.
But it cannot protect you from the fundamental fact that you are living every second of every day in 38% gravity. You can't 3D print a new gravitational pull.
Exactly. This is the physiological toll we touched on during the 7-month journey, but now it is compounded over years or even decades instead of months.
Right, because now you're staying there.
Our bodies are incredibly dynamic systems that constantly remodel themselves based on the physical stress they experience. In 1G, here on Earth, every single time you take a step, the physical impact sends a signal to your bone-building cells, which are called osteoblasts, to lay down more bone tissue.
It's a feedback loop.
Yes. It signals your muscles to maintain their mass to carry your weight.
So what exactly happens at a cellular level when you spend 5 years in 38% gravity?
What's fascinating here is the precise mechanism of mechanical offloading.
Mechanical offloading.
When you reduce gravity by over 60%, the mechanical stress on your skeleton drops dramatically. The osteoblasts, the builders, essentially go on strike because they aren't receiving the signals that they are needed.
I think their job's done.
Right. But the cells that break down old bone, the osteoclasts, keep working at their normal pace.
Oh, no.
Over years, this active dismantling outpaces the building. This leads to profound, accelerated osteoporosis. A simple trip and fall on the Martian surface while wearing a heavy suit could result in catastrophic, complex fractures that cannot heal properly in that environment.
Wait, if the bone is breaking down at that rate, where does all that calcium go? It doesn't just vanish, right?
Excellent point. No, it doesn't vanish. It gets flushed into your bloodstream, and your kidneys have to filter all that excess calcium out, which drastically increases the risk of severe kidney stones.
Kidney stones on Mars.
Yes. Passing a severe kidney stone on Earth is agonizing. Passing one on Mars with limited medical supplies and a 40-minute communication delay to a doctor could be a mission-ending medical emergency.
And it's not just the bones, right? I mean, the fluids in the body behave differently, too.
Yes, this is a major concern. On Earth, gravity constantly pulls the fluids in your body down toward your legs. Your cardiovascular system has evolved to pump hard against that gravity to get blood up to your brain.
Yeah.
In 38% gravity, that downward pull is vastly reduced, but your heart is still pumping hard. So the fluids in your body shift upward, pooling in your chest and head.
So you constantly feel like you've been hanging upside down on monkey bars.
Exactly. Your face gets puffy, your legs get incredibly skinny. Astronauts call it bird legs. But more alarmingly, that fluid shift increases the hydrostatic pressure inside your skull.
Pressure inside the skull, that sounds bad.
It is. Over time, this increased intracranial pressure pushes on the back of the eyeball, literally flattening the shape of the eye and swelling the optic nerve.
Flattening the eyeball.
Yes. We've seen this in astronauts on long missions on the ISS. It's a condition called Spaceflight-Associated Neuroocular Syndrome, or SANS. Their eyesight permanently degrades.
So we have degrading, brittle bones, kidney stones, a weakening heart muscle because it's on a permanent vacation, and failing eyesight due to pressure in the skull.
It's a systemic breakdown.
Yeah, and we still haven't talked about the radiation debt on the surface. Because even if you build your brilliant microbe concrete habitat deep underground to block the cosmic rays, you can't stay down there forever. You have to go outside.
You do.
You have to conduct science, maintain the solar panels, fix the rovers, explore the surface.
And every single time you step out of that underground bunker and onto the surface, you are accumulating radiation debt.
Debt.
That is the correct medical term for it.
Yeah.
Debt. Radiation exposure is strictly cumulative.
It adds up over time.
It does. The slow accumulation over years on the surface significantly increases the conditional risks of severe cancers. It causes double-strand breaks in your DNA, and while human cells have incredible repair mechanisms, those mechanisms can easily be overwhelmed by the constant, unyielding flux of galactic cosmic rays.
So we're dealing with the ticking clock of cellular damage, and then, beyond the physical breakdown, there is the mind. The psychological effects of permanent, unyielding isolation.
The isolation factor is huge.
I really want you, the listener, to try and put yourself in that exact environment for a moment. Imagine waking up every single day for years. You look out a tiny reinforced window and you see nothing but jagged red rocks and a butterscotch-colored sky.
No greenery.
No trees, no oceans, no rain, no birds. And you know, with absolute certainty, that rescue is millions of miles away.
The psychological isolation is profound and entirely unprecedented in human history. On Earth, even in the most remote places, like a submarine or an Antarctic research station, you know you are still on your home planet.
You can walk outside eventually.
Even the Apollo astronauts who went to the moon could look up and see the Earth looking huge and vibrant in the sky. On Mars, Earth is just another bright star in the night sky. It's the pale blue dot.
Yeah.
The realization that every single human being you've ever known, every piece of art, every ocean, every breath of fresh air is trapped on that tiny, distant point of light. The cognitive dissonance and emotional weight of that separation is something we don't fully understand yet.
But researchers are actively trying to figure out if we can handle it before we actually send anyone. The sources mention that right now, between 2025 and 2026, certain space agencies are running year-long analog missions to study exactly this psychological friction.
Yes, these analog missions are a crucial part of the preparation. They take a highly vetted crew, place them in a simulated 3D-printed Martian habitat located here on Earth, and isolate them completely for 378 days.
Over a year.
They enforce the 20-minute communication delays with their simulated mission control. They trigger sudden equipment failures and resource scarcity to see how the crew reacts under pressure.
They basically lock them in a tiny box for a year to see if they break.
Essentially, yes. They're studying the group dynamics, the conflict resolution, and the cognitive decline that comes from extreme monotony and isolation.
Because it's the same faces every day.
Exactly. Because when every day looks exactly the same, and your social circle is restricted to the same 3 people for years, the human brain can begin to struggle with memory and emotional regulation. They are trying to map the breaking points of the human psyche before we send people millions of miles away.
But I have to point out the fatal flaw in those analog missions. Even an analog mission on Earth has a safety valve. If someone has a severe medical emergency, or if someone completely loses their mind, they can just open the front door.
That's true.
On Mars, that door opens to a freezing vacuum and boiling atmospheric pressure. You cannot tap out.
Right.
So we're looking at this overwhelming biological, physiological, and psychological problem. And we have to ask the honest, brutal question, can human biology actually survive long-term on Mars?
And that is a debate that nobody in the scientific community is currently winning.
Nobody knows for sure.
No. The optimists look at the incredible track record of human adaptability. We have survived in the freezing Arctic. We survive for months in submerged nuclear submarines.
We adapt.
Conditionally speaking, if we develop highly advanced pharmacological interventions to trick the bones into staying dense, if we create massive artificial gravity centrifuges inside the underground habitats where crews can sleep in 1G, if the radiation shielding materials take a massive leap forward, perhaps our biology adapts.
I hear that, but the pessimists look at the raw, unbending numbers. The constant radiation, the unyielding 38% gravity. I genuinely feel the pull of the dream. I want to see humanity spread across the cities. But when I look at the physical pole we've just laid out, I have to admit deep, profound uncertainty. I am not convinced that the human body, which is entirely calibrated for this exact planet, is capable of long-term, multi-generational survival outside of a 1G, heavily shielded environment.
And I am equally uncertain. We simply do not have the data.
We don't.
We have data on zero gravity from the ISS, and we have data on 1G on Earth. We have a massive blank spot in our medical knowledge about what partial gravity does to a human body over a decade. We certainly don't know what it does to fetal development or childhood growth.
No, wow. Yeah, children.
Could a human child even develop a normal skeleton on Mars? We don't know. We must frame all conclusions about survival as heavily conditional because right now we are dealing in hypotheses, not certainties.
Which brings us to a dead stop, a philosophical roadblock. Let's pause the logistical and biological debate for a moment.
Okay.
Let's assume conditionally that someday, maybe a century from now, all the engineering hurdles are miraculously cleared. We figure out the radiation shielding. We figure out the medicine to keep our bones strong and our kidneys clear. We build the underground bioplastic cities with microbe concrete.
Assuming all that, yes.
If we can do all of that, does that mean we should go?
If we connect this to the bigger picture, we are leaving the realm of engineering and entering the realm of planetary ethics. And it starts with a deeply contentious concept called forward contamination.
Forward contamination.
Ayash.
Meaning us bringing our earthly mess to a pristine alien planet.
Precisely. If we knew for an absolute fact that Mars was entirely sterile, if it was just dead rock, freezing carbon dioxide and ice, then the ethical calculus is relatively straightforward.
It's an empty lot waiting to be built on.
Right. But we do not know for certain that Mars is sterile. It might have microbial life. Perhaps it's dormant, waiting for a warmer climate cycle. Or perhaps it is living deep underground near hydrothermal vents or subterranean aquifers.
And if it does have life, even just the simplest single-celled microbes clinging to existence under the ice, our arrival could be an apocalyptic event for them.
It really could.
Because we are fundamentally walking biological hazards. We are covered in Earth biology.
We are walking ecosystems. Trillions of bacteria, viruses, and fungi live on our skin, in our guts, and in our breath. No matter how meticulously we try to sterilize a spacecraft, humans are inherently dirty.
We shed bacteria everywhere we go.
When we land on Mars, we bring Earth's entire microbiome with us. If Martian life exists, introducing aggressive, highly evolved Earth microbes into its delicate ecosystem could contaminate it irreversibly. Earth bacteria could outcompete Martian life for resources or prey on it, destroying it entirely before we even have the technological chance to study it.
It's the ultimate prime directive problem, like in science fiction. Do we have the right to permanently alter, contaminate, or potentially destroy another planet's native biosphere just because we want a second home?
And this is not just a philosophical thought experiment discussed in university lounges. It is actively driving current scientific policy at the highest levels.
Right.
The source material highlights a highly significant report published in December 2025. Certain scientific bodies have recommended that searching for existing life should be the top priority of any human Mars mission.
Meaning, before we start building cities, before we start mining the regolith with tractors, and certainly before we start spreading bioengineered algae everywhere to make oxygen, we have to look extremely carefully for what is already there.
Because once we contaminate the planet, we lose the opportunity forever to answer one of the most profound, universe-altering questions in the history of science.
Did life arise independently on a second planet in our own solar system?
Exactly. If we accidentally seed Mars with Earth bacteria and then find life in a soil sample a decade later, we won't know if it's truly an alien genesis or if it's just something that hitchhiked on the tread of an astronaut's boot. We would muddy the scientific waters forever.
But on the exact opposite side of that ethical coin is the backup civilization argument.
Yeah.
This is the idea, championed by several prominent researchers and space advocates, that humanity has an ethical obligation to its own survival above all else.
The argument is essentially about existential risk management. Earth is beautiful and perfectly suited for us, but it is vulnerable.
Very vulnerable.
We have a geologic record proving that asteroid impacts happen. We know supervolcanoes exist. We face global pandemics or human-made catastrophes like nuclear war or severe runaway climate change. As long as all of human history, art, consciousness, and biology is contained on a single fragile sphere, we are a single point of failure species.
It's the old saying that dinosaurs didn't have a space program, and look what happened to them. If you want to ensure the long-term survival of human consciousness, you have to become multiplanetary. You have to back up the hard drive of humanity on a separate server, so to speak.
So we are weighing two massive ethical imperatives against each other. The ethical weight of potentially contaminating and destroying an alien microbial ecosystem against the ethical weight of securing the long-term survival of our entire species against extinction. Both hold immense gravity.
It is a phenomenal clash of values. I feel the heavy pull of both arguments simultaneously. The dream of exploration, of pushing over the next hill, of securing humanity's future in the stars, it is such a powerful, almost intoxicating narrative. It feels baked into our DNA.
It is a compelling vision.
But the ethical weight of treating another planet like a vacant lot waiting to be paved over and colonized, that gives me serious, profound pause. I don't want human expansion into the cosmos to just be an interplanetary version of an invasive species taking over a fragile ecosystem.
And that tension between ambition and caution is exactly where we currently stand as a species. We are caught squarely between the awe of what our engineering might achieve and the profound caution demanded by biology, physics, and planetary ethics.
Let's summarize where we've been today, because we've covered a massive amount of ground in this deep dive. We started by entirely stripping away the sci-fi romanticism. We looked at the terrifying, brutal physical reality of the Martian surface, the minus 60-degree average temperatures, the boiling point of water at 1% atmospheric pressure, the relentless barrage of cosmic radiation, the electrostatic dust storms, and the creeping, insidious degradation of 38% gravity.
We examined the harrowing 7-month journey just to get there, enduring the equivalent of 24 CT scans of radiation every single day, while our bones and cardiovascular systems actively weaken in microgravity, all while being completely isolated by an unforgiving 40-minute communication delay with Earth.
But we also looked at the staggering, almost unbelievable ingenuity being proposed to solve these exact problems. We talked about growing habitats from living algae in 3D-printed bioplastics to create closed-loop oxygen systems.
The biomineralization as well.
Right, using tough microbes to literally cement the Martian soil into biological concrete. We looked at the brilliant engineering that might allow us to build a living, breathing fortress in a frozen wasteland.
Yet we balanced all of that mechanical ingenuity with the unresolved fundamental question of our own biology. Can the human machine, a complex organism evolved strictly for the heavy gravity and protective magnetic shield of Earth, genuinely survive and thrive for decades in the hostile physics of Mars?
Conditionally, perhaps, but certainly not easily, and certainly not simply.
No, it won't be simple.
Mars is not simple. It is not imminent. And as we've just discussed, depending on what might already be living in the dirt, it might not even be entirely ethical to go. Which leaves us with a lot to think about the next time we step outside on a clear night and look up at that distinct red dot in the sky.
It really does.
We've explored the bleeding-edge engineering. We've debated the harsh realities of biology. But I want to leave you with a thought about the philosophy of it all. You know, earlier I asked you to imagine standing on Earth, looking up at Mars as the ultimate frontier. Now, I want you to imagine standing on Mars, looking back at the pale blue dot of Earth. If we figure out all the biology, if we solve the radiation shielding, if we build the underground cities and master the gravity, if you figure out how to survive on Mars, does that mean we should?